So here we go, and welcome to the third session. How many of you have watched the video? I'm sorry, I've been, a bit kind of semi-watched it. All right. Well, I do have the option of going through the main points of that as well. Would you prefer that?
Yeah.
Shall we just go through the main points? All right. Let's do that. Okay, so the topic there, well, calculating correlation, bloody hell. There are a few things which are a bit over the top in the slideshow, as you understand by now. So I'll just go quickly through the bits that relate to objects. So the main thing to understand is how the size of the object in relation to the wavelength is crucial. Okay, so the objects pose different type of resistance, obstacles or none, based on their size. Okay, so everything we do pretty much in acoustics relates to the fact that we hear frequencies between about 20 hertz until about 20K, and these relate to certain distances. And these distances or these wavelengths will have some relationship to the object. So the main basic thing, which is quite intuitive, is that if you have a wavelength the size of this room, right, then a table like this won't do much. Okay, so that's what we're looking at. And also the other thing to consider is that the walls of certain thickness also won't do much. So it's not just the dimensions of objects that is crucial, but it's also the thickness of objects in terms of actually blocking the sound. So you're probably aware of the fact that bass is really difficult to block, right? Technically, we can do this better with very thick materials and very heavy materials, but we can also do it with layering of materials. Why? So this is something you might remember from the first class. What is it about layering materials that makes a boundary acoustically more optimal? Yes?
Is it overlap gaps in
The changing of density, yeah, exactly. So how did we call this? What is changing? It is the acoustic impedance. Okay, so that was this really important thing from the first class, that if you have an abrupt acoustic impedance drop or rise, then this will reflect acoustic energy, right? So the good old ball does not bounce off of an open window, but sound does. Right? So it's not just the sudden increase in acoustic impedance, but also the sudden drop of it. Okay? And this will actually be quite relevant to what we are looking at today. So, well, what I'm going to quickly go through today, the reflection, and then essentially the diffraction will be one of those things which are a bit puzzling to start with. But actually, if you understand that the sound bounces off of the open window, then you can also imagine that if a sound wave is traveling along a surface and suddenly the surface stops to exist, something will happen there as well. And it will. So actually that's why you will find that certain speaker manufacturers, they make rounded corners to the speakers. Because if you have a hard edge at the speaker, thank you, Max. Sorry. If you have a hard edge at the speaker box, you will get anomalies, more so than if you have a rounded edge. Okay, so we'll discuss briefly then how the objects, what do they do to sound. Okay, so here is a little model with balls and springs that we've looked at previously. So what you have then is that of a boundary, the compression which travels, so to speak, between the balls, right? So the balls don't travel, but the area of compression does. As it reaches the wall, it actually starts to travel backwards. Okay, that's fairly straightforward. Now, the thing to note is, I'm not sure, I don't think I have this. Yeah, here is the two types of reflection. So the point is that if I have a solid wall, right, then the compression starts to, you can imagine this intuitively, kind of reflect back immediately. But instead, if I have an unbounded region here, so I don't have a wall, I have an open window, so to speak, then what happens is that this last ball swings away first and then comes back to the previous one, and it travels again back as a compression. Okay, so that's what happens. And actually, you can imagine that there is a bit of a time difference. There is a phase difference in this reflection. Okay, so off a bounded region, what you see is that you get a reflection in phase, whereas here we get a reflection out of phase. It kind of bounces away. Okay, so that's also kind of hopefully, giving you the intuition as to why on earth does the sound bounce back off an open window, right? Okay, so those are the bits about impedance. There are some really nice visuals produced by some physics professors here. And here what we can see is what happens with, I haven't looked at this for a while. So it is supposed to give me a reflection. Okay, so what happens when you have a wave traveling and coming to an impedance boundary? Okay, so I have one medium, the second medium. Okay, and this is done, the simulation is done by highlighting, kind of approximating the reflection by dots. Okay, and the fact that some energy will reflect back and some will come through. So if I restart this, you can watch it again. The interesting thing is that the angle of incidence, or the direction of travel, will actually change. Oh, I didn't do the next step here. It is a bit flimsy, this thing. But it shows it quite well that actually what we do is we approximate this reflection by looking at what happens at each point, right? And then you see that this angle of incidence is changing, and also the speed, the velocity is changing. Yes?
That initial line.
Yeah.
Is that the wave front?
Wave front, exactly.
The refractions that it's showing the curves.
Yeah.
The line you can see at the bottom of the red one, is that the next wave?
Exactly. This is the transmission of the wave front, right? So actually, I talked about this briefly. It's worth iterating how we can consider sound something like an arrow that has a direction of travel, but we can also consider it something like a wave, right? And this much depends on whether we're looking at high or low frequencies in terms of which one is more useful. And when we look at low frequencies, we are better off considering it a wave. And then the first line that describes this wave is the wavefront. Okay? And it's a really interesting thing potentially as well, when you cross the speed of sound, as you do, right? You actually burst through your own wavefront. That's what causes the explosion, right? Because, and that's a nice way of potentially connecting it to the Doppler effect. Everyone is probably aware of the Doppler effect, right? So when you have a moving sound source in relation to the receiver, then while the sound source is approaching, you hear it at a higher pitch. And when the sound source is departing, you hear it at a lower pitch. So that's your, you have a pitch drop as it crosses or as it starts to depart from it approaching. So you can also visualize this wavefront. So if I am projecting sound as a static source, right, then the wavefront, let's say of this clap, is a circle, right, a sphere that grows, and it's symmetrical. Now, if I am moving, the moment that I've produced this wavefront, I've actually let go of it, so to speak. So I cannot modulate that wavefront anymore, but I am moving, right? So actually, if I do this and start to move really fast, then I'm catching up with my wavefront in one of the directions, okay? Now, if I'm continuously emitting a sound, then actually in the direction of movement from the perspective of my target, right, the wavefronts are being compressed. Because if I emit the first wavefront at this position and then at the next position and the next position, right, those wavefronts will actually be that much closer together. And that's something that you can visualize as a higher pitch, as a higher frequency. The troughs and the peaks are more compressed in time. They come after each other sooner, right? So I'm actually, if I'm moving, then I'm compressing the wavefront in relation to my target, but actually I'm expanding the wavefront in relation to my point of departure, right? Because it's the same mechanism. I'm moving forward, and each time the next wavefront will actually be centered around a different center position, and thereby have moved forward. So actually I get a lower pitch. Okay? Cool. Now let's see what are the interesting things here. So if you have two boundaries, and that this kind of goes hand in hand with today's topic, which is rooms, what you get is you get standing waves. So there is, I believe there is another lovely diagram that shows you how actually the standing waves can be understood to be made up of reflections. Okay, so first of all, just to try and solidify this term, standing wave, and its counterpart, which is traveling wave. Okay, traveling wave is probably the easier thing to grasp intuitively. It is when I have a huge rope and I make a nick into the rope, and what you will see is that this nick actually travels with the length of the rope. Okay, so that's a traveling wave. Now a standing wave is the one where the peak does not move visibly, but actually just goes up and down. Right? So that's what's standing about it, which is a bit potentially confusing because actually it's a wave. So something is moving. So what the hell is standing? But that kind of trough propagation or peak propagation is not happening. Okay? Nevertheless, what you can observe here is, hope I press these things well. Okay, so that if I have a wave coming in, so this is currently a traveling wave. It will take a while. Incidenting single steps. Well, I'll just wait for it. Okay, so what we're observing then is how this wave will reflect. Okay, so what you see is that it's reflecting in opposite phase. Okay, and then because it interferes with itself as it reflects, right? What you're getting is a constructive interference, so you get things to become louder. And the other thing that you observe is that the summation of the two waves, so the forward traveling and the reflected wave, the summation of these two waves appears to be standing, right? So this is how the traveling wave with the reflection actually mounts to become a standing wave. Okay? Now, the other thing about standing waves is that they become the resonance of the room, which we will come to. And this graph also helps us understand the difference between velocity waves and pressure waves. Okay? So the point is that the easy thing to understand is what happens at a boundary, at a fixed boundary like this. So the point is that the velocity of the particles is minimal because they are bound physically. They cannot move as much, right? But the pressure is the highest. And these two relate, right? So if I have a lot of potential but I can't move, the pressure mounts. Put it in simple terms, okay? Now, the other thing that this relates to is the fact that our ears are pressure devices. Okay, they're not velocity devices, and this is something which is quite interesting if you study further potentially into electroacoustics. But that's one of the reasons why, for us, standing next to the wall makes the sound louder, right? In particular, the bass. Next to a wall, it is always louder for us. There is more pressure. Okay? So I kind of hinted at this. There is a 90 degrees offset between your velocity and pressure components. Does get complex. Okay. Right. I'll skip the next one. Okay, so this would be some kind of an exercise. I didn't really read through this slide before because I didn't expect to do it, but never mind. So what we have here then is tube which is open at both ends. And for this class, I would typically bring in a vacuum tube. And this is the kind of space where there might be, do you see a pipe of some description somewhere? Because there's a really interesting experiment to be shown how things are different. Let's see, is there a pipe? Is there a pipe? Not quite. I hate to dismantle anything, although I probably could. Take this. Anyone has a set of Allen keys? So the experiment, I'll tell you about it, then you can try it at home with your array of pipes. Typically, it's good to have a fairly long pipe, maybe like a Hoover pipe. And what you do is, if you strike it and leave your palm on the pipe, you will get a different frequency from if you strike it and immediately open or actually kind of bounce off with your hand. Okay? And this is something, actually I normally spend more time on this with instrument recording investigation because it's pertinent to instrument acoustics. Okay? So what you would get is a kind of a different response from this. But this is kind of going a bit deep, and this kind of phase inverting reflections or not, let's just leave it as an interesting thing. In any case, if you have asymmetrical boundaries in pipes, things happen differently and you get different frequencies, but that will come in instrument acoustics. Okay? Now, if you can imagine a standing wave, hopefully you can imagine a two-dimensional standing wave as well. Okay, so this is something that can happen, and obviously there will be three-dimensional ones as well. We'll come to that in a second. Okay, so here comes the diffraction. Now, simply put, bending around sources, right? If this is a sharp corner. If it is not as sharp, things behave slightly differently. Okay? And what you have then is that this also will depend on the frequency, or more precisely, on the relationship between the frequency and the object dimension. Okay? So you can actually scale this up. So if something happens, you know, at an octave above, the same thing will happen for an object twice as small. Okay? So an octave is a twofold increase in frequency, right? And therefore half the wavelength, right? So it will interact with half the size object in the exact same way. And as you might expect, what happens here is that if the frequency is lower, you get more bending, right? If the frequency is really low, it kind of engulfs the object. It doesn't really see the object as an obstacle, okay? And that's the graph of that, right? So the amount of diffraction in relation to the frequency of the wave. Cool. Now, there is a whole lot of interest in slits in physics, also for electrons, but also for waves. And the point is that we get these interesting interference patterns or not. And then there's this whole interesting bit about how do you get an interference pattern from a single electron or a photon that you shoot through a slit. So you get an evidence that actually a single photon does behave like a wave, by the way. So we're kind of back at the beginning where I said, well, both waves and particles are cognitive models, are things that are born in monkey brains, and it's just lucky, or it's probably the reason why they are born in the brains, is that they really match the environment quite well, but they are not the environment. Okay, so there is a lot of interesting things around this. I won't go deeper into this. You have these animations there for you to observe. Okay, so just as we had slit diffraction, we have diffraction around the objects. And this is where you see it, that if the frequency is really low in relation to the size, then it's almost as if it wasn't there. Okay, now talk briefly about scattering. Scattering is the phenomenon whereby we have non-specular reflections. Okay, so that's a neat, crucial term, specular reflection. It's probably on one of the previous slides. And it covers the kind of reflection you expect on a pool table, right? So you have an angle of incidence, right? You have the angle of reflection, and the two angles are the same. Fairly straightforward. The interesting thing is about specular reflections, if you have a 90 degrees corner, then you will actually get a parallel ray back, right? So I don't know if anyone is playing your Belgian carambole billiards, which have no holes, no pockets. Actually, it's my favorite. All these potting balls is a bit of a ball ache. Ha. And I prefer this kind of more combinatorial thing. So you have this billiards game where you have no pockets, but your task is to hit 3 walls before doing something else with the other ball. So you're really, really concentrated on these reflection angles, and then the spin on the ball affects it quite a bit as well, and it's a bit more interesting game in my view. So what is scattering? So non-specular reflection. So why does this happen? Well, it happens because of the material properties, but it also happens because of texture, some kind of grain to the boundary will cause certain frequencies to scatter. Okay? Now we have two terms. We have scattering and diffusion. Okay, scattering is the term that really covers the reflection aspects, whereas diffusion could be messing the phase otherwise as well. Okay? Normally it has to do with reflections as well, by the way, but it could be some material properties which make the wavefront more diffuse. So what is a more diffuse wavefront? Well, visually, now that we're kind of, have this line in mind which moves forward, it's diffuse, so it's not just a clear line. There is something to it, some randomness to it. Now, technically, we distinguish between these two terms. We actually have scattering coefficients and we have diffusion coefficients. Okay? And the difference there is that the scattering coefficient will say how much energy has been reflected in a non-specular fashion, in a random angle, so to speak, whereas the diffusion coefficient will tell us how evenly random the scattering is. Okay, so it kind of comes as a term on top. It does not just deal with, well, there is a lot of odd reflections, but how even is the energy reflected in all possible directions. Okay, so a high amount of scattering could mean that I just have a really bad angle reflection, but high degree of diffuseness means that after the reflection the energy is scattered in all possible directions evenly. Right, so it tells you a bit more about the character of non-specular reflection. Okay, those are the crucial terms here. Now, resonance is a term that you probably understand quite well. The interesting thing about resonance, obviously I invite you to watch further and play with these models as well. But the interesting thing about resonance is that it is decepting or deceiving, or both. Deceptive or deceiving. What's the difference between deceptive and deceiving, guys? Any clue?
If you're doing it, deceptive is something is already...
Oh, I see. Oh, great. So it's deceptive because it's not active like that. Great. So the thing that happens is that we typically, when we encounter resonance, we might say that things become louder. Okay? So if I ask you, how does a stretched string sound when you add the guitar body to it, right? Well, most likely you're going to say it becomes louder, right? Now, this is not necessarily an issue because loudness is a psychoacoustic term, and if you hear it louder, it is louder no matter what. But the interesting thing is that technically, you might understand that the guitar body is not an active entity, right? It does not add energy. So how on earth does it make sound louder when it does not add energy? In fact, it can only absorb some energy. The only thing that can happen, it can actually become softer in that sense. Any ideas? How on earth does this happen? Yes?
Are the waves interfering with each other to increase the volume?
No, I wouldn't say so. No, not necessarily, because it is not about the reflected wave. It is about the mechanism that produces the sound. And it is a resonant mechanism. So what is this resonance? Yep.
Is it to do with the being a quarter of the wave ahead, like the leading force is a quarter of the same way that the velocity in the...
No, it's not really that. It's not really that. The hint here is bandwidth. So what happens with resonant objects, which are typically passive, right? So that's this riddle. How on earth does it happen that it's much louder, but there is no invested energy. The clue is in bandwidth. So what the resonance system has is a very narrow bandwidth resonance response, which means that if I have a lot of acoustic energy which is spread out across the spectrum, it is fairly flat. If I drive it through a system which is resonant, then what happens, it kind of sums all the energy into that frequency band, right? So the total amount of energy may not be larger, obviously, because it's a passive system, there is no added energy, but certain frequencies become louder, okay? Or maybe if it's a very clean resonator, just that one frequency that it resonates at becomes louder. It kind of sucks up the broadband energy, right? And makes it a narrow band energy. That's the property of the system. Actually, it does have to do with how it internally reflects things and the dimensions of things, creating these back and forth motion patterns and all the rest. So it does kind of have to do with dimensions and the reflections. But actually, what it is, from a larger perspective, it is a bandwidth trick. Okay? Cool. So briefly, Helmholtz resonator, a bit of physics. It's really interesting. You can do this. I used to do it in class as well. Get a few wine bottles and then measure the resonant frequencies, blow across them. Calculate the resonance frequencies, then blow across them, measure the resonant frequencies, compare the two. It kind of computes, right? Wine bottles are cool because the volume is typically the same. So then you can make some conclusions about the neck, which is crucial in this system. The neck here, the air in the neck acts a bit like a spring. Okay, so that's one of those broader things to get excited about. The fact that every acoustical system can be translated into an electrical system. So things like capacitors, coils, and resistors have their counterparts in acoustics. So you can kind of translate between the two, right? And then potentially also interesting is that you can translate it into a digital model as well, right? So these things are, and that's what we call electroacoustics. So if you really get into the engineering of this, it is quite exciting. So in essence, everything that you build from electronic circuits could be made an acoustical system. In fact, one of the earliest voice synthesizers was actually a source of pitch, a broadband source of pitch, matching the vocal fold pitch, probably around 100 hertz. And then what you had is a flexible tube that you could squeeze in multiple places. And by doing this, you would actually get different formant frequencies. And if you did this well, you can kind of create a vowel-y type sound or transition between different vowels. Okay? So in that sense, you're kind of creating filters by squeezing the tube in different places. Okay? An interesting thing you might want to try. And then, well, the next level, if anyone wants to stay on for a master's degree, I think we can offer masters by research in this department. There's some really exciting things over in Q Block with our unconventional computing research center, of which I'm a very tiny part called the unconventional audio signal processing. And there's a lot of things to do with sending signals through different substrates and discovering different media, what they're doing. There are microscopic structures which do very weird things as well. So there's quite something to say about how, maybe even a synthesizer, which is an electronic circuit, could not just be translated into an acoustic set of objects, potentially tricky but possible, but even into some kind of a biological or colloidal. Colloids are one of these things on microscopic level that do weird stuff. So we'll see where it goes, but there is good likelihood that audio will kind of move slowly away from electronics. In fact, you can buy. There is a guy in Greece who's already selling, Eurorack modules, and you have ones which actually work with electrolytes. So it's a kind of a liquid synthesizer in a sense. So there is all of the systems around us have some interesting properties in how they respond to vibration. So with a bit of luck and a bit of cunningness, you can probably get the sound to go through many different things. The interesting thing is always the nonlinearity. Okay, but this is something which is kind of off topic here, so I will just leave it at that. Okay, so that was briefly about last week's, and then briefly about this week's content. Again, I will attempt to finish fairly soon. These questions are a bit advanced, so I'm just going to leave it for you if you're interested. So combining decibels, I kind of talked briefly about this, not hugely pertinent anymore. Here we go with the rooms. So first of all, a bit about absorption. I've already talked about reflection, some room properties, reverberation, and natural modes. Okay, so this is a fairly important graph to keep in mind. I believe I've hinted at it previously, and it describes what happens to acoustic energy when it reaches a boundary. And there is three things that it can do. It can reflect, it can transmit, and it can be absorbed. Okay, so this is fairly straightforward, but normally when we think about things in acoustics, we typically forget one or two of these. Okay, so I think I mentioned this, that if you want to have a better response of a room in terms of acoustics, you want to avoid reflections. Okay, reflections will mess it up. So how do you avoid reflections? How do you lower the reflected intensity? Well, you have two options. You either increase the absorption or you increase the transmission. Right? That's the bit that we typically forget, that when something is transmitted, it's actually not reflected. Okay? Now, evidently, the properties of the materials will define how this pans out, especially with at different frequencies. So here's a bit about coefficients, because each of these paths is represented by a coefficient. I won't bore you much with that in terms of figuring out how do they relate to each other. Nevertheless, absorption coefficient is quite crucial to understand, because you might be finding data sheets with absorption coefficients. In fact, if you do some of our basic reverb time calculations, they ask for absorption coefficients. Some of the more elaborate room mode calculators or room simulators will also ask for absorption coefficients, but it's also just useful to be able to compare materials in terms of their absorption. What's missing? If I tell you this carpet has an absorption coefficient of 0.2, what is potentially missing about this statement? Just to get your analytic, skeptical juices flowing. At which frequency? Okay, so that's also worth looking at, because it might be that you're looking at a spec sheet with absorption at 500 hertz, right? It might be that they're actually giving you an average of a broadband absorption. and so on and so forth. So as you can imagine, high frequencies are much easier to absorb. And therefore, a single absorption coefficient will not describe fully the material that you're dealing with. It describes a certain aspect. So if you have a chance of having a look at the spectral absorption across the audible spectrum, that's a good idea. Okay, so perfect reflection is 0, perfect absorption is 1. Okay, well, mind you, it says open window. Haha, that's funny. The size of the window may cause that certain things are actually reflected back, and it's also the space outdoors versus the space indoors. So this is actually a bit of an approximation. But anechoic chamber, definitely, if it's fully anechoic, everything is absorbed. You get an absorption coefficient 1. Okay, so here is a bit about your reflections. Now, the interesting thing to note is that whereas this kind of phantom image works for light, right? If I have a mirror, I actually see something behind the surface of the mirror. With acoustics, it does not really work. Why not? Yep.
Is it this, for that to happen, there's usually like the direct waves coming straight at you, and not just the bounce one. So you'll hear that one as well as the.
Yeah, definitely. There's a bit of this. There's actually many things that play this game or play with it. The other thing is that typically sounds are broadband, okay? Typically your reflectors will behave differently at different frequencies, so something or other, something odd might happen. The second thing is that you see here we're looking at arrows. And you saw previously this animation when these arrows kind of made up a wavefront as well. So you kind of see how these two relate. But if you imagine that a sound source projects a really complex spectral characteristics in all possible directions, you know, then you understand that it's really far away from being an arrow like that. And there is also something about the geometry of the wavefront that is apparent, because if it is what we call a flat wavefront, then you kind of get this geometry back, but if it's not, it's getting skewed. Okay, so it really depends on the environment. It may seem that the sound is coming from beyond the wall, but it's much less likely than in light. Okay, so in this reflection, the crucial thing that we're considering is the path difference, right? So what we get then is the summation of correlated sources. Well, technically it is a single source, but the two wavefronts are correlated, and there is a delay time between the two, which relates to the path difference. Okay? So when you have summation with the path difference, what you get is comp filtering. Okay, and this is something that I kind of, sometimes I'm inspired and can draw this quite well in terms of why on earth does it happen at multiple frequencies. Okay, so far it is potentially evident that this destructive interference kind of makes sense, right? Things are out of phase. If they sum together, they might extinguish each other, but typically in real world environments attenuate, at least. This brings me briefly to one of those lovely riddles that I have, is that in acoustics 1 + 1 is how much? 1. Yeah, right. So just to show you how things add up differently, right? So if you add one sine wave and another sine wave of the same frequency, you get a single sine wave. 1 plus 1 is 1 like that. Okay? I mean, it's a kind of a provocative statement. It's a bit funny. It's almost like a pub talk at this stage. But it really shows you how you really need to find different ways of thinking about things, because sounds don't add up like apples and pears, and you cannot separate them like apples and pears. So once you've projected two sine waves of the same frequency into a space, there is no way of figuring out or separating them apart, right? They kind of fuse, right? So that might be a good term. So the sound does not add, the sound fuses. Kind of makes sense. But the question that we're looking at here is, why do we get multiple notches? Okay, and the reason is, actually I probably just try and draw this. I'm not sure, probably the camera won't catch it, but never mind. So the point is that a single distance, I'll pick this one. Let's call this my path difference. So this is the length of space, the length that one wave has to travel more than the other before they sum back again. Okay? So the basic situation is that if I have a, let's start with the basic most, right? Let's say that this corresponds to a full wavelength. Okay? So if this is the amount of delay, that means that the B wave has been delayed that much to become the A wave, and then they sum back again, and you see it already, it is constructive interference. So they will add up, and they will make things appear louder. I noticed that you probably don't see the green one at all, so I'm gonna just remove that. Okay? Now, the thing is that if I have half the frequency, in fact, I'll just make this a bit shorter, maybe my drawing will be more accurate. So if I have half the frequency corresponding to this wavelength, then an A wave like this is delayed that much and becomes this, but by this time this one is going down again, so I have exact out of phase destructive interference. Okay? Now this is the lowest frequency at which I get the notch. But actually what happens is that if I have 3 times the half, so 3/2 wavelength, which means I go up, down, up, and almost down again, then this wave will continue like this, evidently. But after this amount of delay, the B wave will actually also be fully out of phase with this one. Right? So I have one frequency which corresponds to half the wavelength, and I have 3/2 the wavelength as the next frequency up, at which again I will have a full destructive interference. Right? And so the row goes. Okay? So this is 1.5, right? I can also have 2.5, which would be my 5th harmonic, so to speak. So if I go up, down, up, and a bit down again. Okay? So if this is the frequency of the wave, after this amount of delay, again I will have destructive interference. So that's why we get this pattern in spectrum, whereby you have notches, an infinite amount of notches, one after the other. You can determine the lowest frequency notch and then take it from there. Actually, you see it on this graph as well, that at the lowest frequency, there is constructive interference. So you actually see that there is some kind of interest in the lowest frequency, in the first notch. And then actually the distance between these notches is linear. Okay, that's another thing which you might find interesting. So they're not harmonics like that, they actually become linearly distanced. And this is what happens then every time there is a reflection and summation at the receiver. Okay, so as soon as you have a reflection, it means that there will be a path difference. If there is a path difference, there will be frequencies which are affected. Okay? So that's what constantly happens. And then if you just imagine how many reflective surfaces are here just between us, and each one of these reflections will give you some or other comp filter type response, what happens then? Well, statistically, they kind of even out. You see? So if you have a very strong single reflection, you might actually hear the comp filter. But if you have many, many different reflective points, you know, overall they will even out. So you don't really hear a spectral anomaly anymore. Okay? Cool. Comp filtering exercise. There you go. Just for your reference. If you want to play with these numbers, check it out. In fact, well, we'll see. We'll see how the practicals pan out, how quickly you go with the stuff planned. But there is an option to do a practical with verifying the comp filter of a reflection, and it's the one that is tricky, or at least potentially impossible even. Really depends. In any case, we won't calculate comp filter notches at this stage. Cool. Right, so we've come to the rooms. Typically, we will consider rectangular rooms for the sake of simplicity. And as soon as they're not rectangular, things change, obviously. Very straightforward. Room volume, you're probably aware of this. Height, length, width, multiply the 3 dimensions, and you get room volume. Now, in terms of the reflections in a room, we can actually figure out the number of them. I probably won't spend the time with this now. But nevertheless, you can figure out, can you do this? Can you figure out the number of first order reflections in a rectangular room? So I have a red dot, which is the source. I have the blue dot, which is the receiver. The red line is my direct sound path. And then the green paths are reflections. And the first order reflections are the one that have met a single boundary on their way back to, or not back to, forward to the receiver. So how many? Well, if you think about it, yeah, you have an idea? 5? Why?
Because it would be all the sides that will accept the one beyond the receiver. Because when they hit the receiver first, it was going to bounce back. So you've got these 4 and the one behind you.
Well, that's the thing. I mean, the sixth one, it is technically a reflection. I mean, I didn't specify that both source and receiver are omnidirectional. If I'd done that, then it would be a more straightforward answer indeed. But well noticed, it actually does depend on the directivity of source and receiver in that sense. Because if I don't receive anything from the back, then that wall is off. If the source is unidirectional, then that back wall is off. So there could be variation, but technically it is the amount of boundaries that will determine the amount of first order reflections. Psychoacoustically, as the reflections progress in higher order, we get slightly different sensations. It is a bit of, you will potentially find someone saying, well, that's how you hear the room size, but a better thing to say is it contributes to our sensation of the size of the space. And you probably know on reverb algorithms we have the pre-delay time, which kind of does a bit of this. You see, because if the first reflection is very late in relation to the direct sound, right, then it took longer to travel. So the time between the direct sound and the first reflection is indeed indicative of space size. Nevertheless, our estimation of space size through audition is hugely complex and should not be simplified like this. Okay, so now we add the second order reflections. We have all the blue lines in there. So what we have then is that they are progressively softer because they have lost energy at increasing amount of boundaries, and they are further delayed because it took more distance, it took more time for them to come to the receiver. We have 30 in total. Why is this? Yes?
Is it because the 6 reflections are bouncing off 6 walls?
Yeah?
So it's causing 30 total?
6 by 6 is 36.
That's true.
Yes?
Is it because it's not counting the wall that it originally reflected off in the first order, so it's technically
Exactly. Yeah. So if I bounce off a wall, I cannot bounce off the exact same wall again, right? So once you've bounced off a single wall, there's only 5 other possible walls left to bounce off of, and that times 4, right? 30 times 4, because once you bounced off 2 walls, there's only 4 left that you can bounce back off. Then you get 120 reflections. So you see how the number of these reflections is dramatically increasing. And as we said, the sound doesn't add, it fuses. It starts to seriously fuse. So actually at this stage we are gradually arriving at what we called the reverberant field, where the acoustic energy is really diffuse. Fourth order, well into reverberation. So if we plot these on a timeline, so to speak, what we get is the impulse response. Okay, so if you look at the impulse response, you are actually looking at all the reflections as they follow each other. But the interesting thing is that you can consider it in this fashion, as in discrete reflections one after the other. But actually, when we produce impulse responses, we actually get a sound wave, which is the response of the room. So it might be kind of confusing to mix them up, but actually they both amount to pretty much the same thing. The way you will make the distinction is that if it is a sound wave, if it's a continuous sound wave, which is the response of the room, what you will have is a bipolar signal. So it goes plus and minus, typically. Okay? So impulse response is a huge engineering subject. It is extremely useful for determining the properties of time invariant linear systems, or linear time invariant systems, in other terms LTI systems. This is a bit of an engineering talk in here. I hope you find it welcome. The point is that when we say a system is linear, what it does, among many other things, and I think this will keep coming back, is one example is A plus B equals B plus A. And 3 times A equals A plus A plus A. So you could think of it such that math holds, math works. When we get to nonlinear systems, we still have maths to describe it, but it's not that simple anymore. Now, in terms of audio, the distinction is even more obvious, even more apparent. With linear systems, we get no new spectral components. With nonlinear systems, we get new spectral components. Okay, and that's crucial. So what you have is that filtering is a linear process. I mean, obviously a desk like the one in the back and otherwise produced weird filters will have some nonlinearities. But what we aim for, what digital filters are capable of delivering, is a linear response, which means that what I'm doing, I'm only attenuating and balancing the existing spectral components. Okay? And here is your terminology hint. Don't say existing frequencies, say existing spectral components. It is actually more accurate. So with a nonlinear system, what you get is, put it plainly, distortion. Distortion is excitation of new spectral components. Okay, and that is crucial. So with an impulse response, we can exhaustively describe a linear time invariant system. So linearity means that there is no distortion. And distortion is a bit of a term which is broadly used, and my mind can be distorted and many other things can be distorted. If you put something upside down, you can call it distorted. So the most accurate way of putting this would be saying non-linear distortion each time I say distortion, but I kind of omit that. Because in audio for us, it's all quite clear what the distortion pedal does, and if you overdrive the speaker, what it does, right? So technically what's happening is that you're going beyond the linear transfer, beyond the range, the dynamic range of the system within which it is linear, and it clips off. Okay, so that's your entry-level understanding here. If things clip, or if things saturate, like a magnetic tape, which means that it doesn't quite clip, but it's already struggling to make the excursion, so it's kind of rounded off, it's compressed like that, right? So saturation as well. These processes are nonlinear because the same increment in volume at the input may not give you the same increment of volume at the output, right? So the basic math doesn't hold, so to speak. And the interesting thing is that as soon as you have a little trace of nonlinearity in the system, a clean sine wave will not remain a clean sine wave. What will happen to the sine wave? It will produce harmonics. Okay? In fact, you might be aware that in an electronic circuit, producing a clean sine wave is near impossible. It's really difficult. You don't get a clean sine analog oscillator. To get a clean sine, we really need a digital oscillator, because there is inevitably some nonlinearity somewhere in the system. We can just not do it, really. Okay, so the sine wave gets harmonics. What do two sine waves get on top of their own harmonics? This is a bit of an advanced understanding, but definitely crucial. We get intermodulation components. So the point is that if I have a single sine wave and I add a little bit of harmonics, second harmonic twice the frequency, third harmonic 3 times the frequency, I assume you understand the harmonic series. If I add just a little bit, I might not notice, right? Why? Well, because our perception has evolved in the environment where things have harmonics. So our perception in terms of sound source identification embraces those harmonics as the constituents of that very source. So it was never trained, it has never evolved to distinguish harmonics from the fundamentals, because they typically belong together in a single sound source. Now, intermodulation components are not integer multiples of fundamental frequencies. They are sum and difference intermodulation components. So if I have a 90 hertz sine wave and a 100 hertz sine wave, okay, I put them through distortion, I will get their respective harmonics, but I will get the sum and the difference. So I will get 190 hertz appearing seemingly out of nowhere. I will also get the 10 hertz appearing seemingly out of nowhere. And I will also get higher order intermodulation components. So I will get 2A plus B, 2B plus A, and the row continues forever. And all of these spectral components are not readily fused by our perception because we just haven't encountered this much. Okay? And that's where you see the A plus B does not equal B plus A, because distortion is a nonlinear component. It is not the same thing whether I have two sine waves, 90 and 100 hertz, which are first mixed and then distorted, or first distorted and then mixed. Why? What's the difference? It's the intermodulation, namely, when do I expect intermodulation and when do I not expect intermodulation? Yeah? That's the other way of calling distortion or summing. So mixing, summing is linear, distortion is nonlinear. So the point is that if I distort the sine wave A, I will get its harmonics. If I distort the sine wave B, I will get its harmonics. So if I first distort them and then add them together, then I will get only their respective harmonics. But if I first add them together and then distort them, then I will get the intermodulation components as well. Okay? And this is something that holds for all nonlinear systems. So you see the order of operations is significant, right? If I do this with a filter, which is a linear component, and if I first filter A and then filter B and then sum them together, it is the exact same thing as if I first sum them together and then filter it. There is no significance in terms of the order of processes, okay, because they are both linear. Mixing is linear, filtering is linear. Distortion is not linear. Compression is not linear. In fact, every compressor is a bit of a distortion, and every distortion is a bit of a dynamics process as well. Right? So that's just to set aside all the things that are non-linear, because actually in acoustics we are looking at linear systems. By the way, the way the things become really interesting in acoustics is also by injecting some non-linearity one way or the other. But how could we do this? Can you think of an acoustical system which is non-linear? Reflection is linear. It does not produce a new spectral component. It can scatter in different directions. It can attenuate certain frequencies. Yeah?
So if you have like moving like boundaries and stuff, so like if you have a speaker on top of another speaker and that speaker's playing, it will vibrate the bottom one in a weird way, which might...
Yeah, you can get this kind of modulations. But actually the funny thing is that everything is nonlinear. Because what am I saying is, if I say that something is completely linear, it just means that I'm using it appropriately. For the musicians, producers in the house, you probably know that, you know, things start singing once you start misusing them, really, once you get to the boundary of its capacity and go beyond. And that is the case with all the acoustical systems as well, right? I mean, I probably would not say many accurate things if I went down the path of describing what happens if I would pump one 10,000 dB signal into this wall. but but it's gonna be in the nonlinear region, right? So everything has a nonlinear region, technically, right? I mean, it's an electroacoustical system, but speaker is a nonlinear thing as well, right? It has the amount of excursion where it's fairly linear, but as soon as it goes beyond, things start happening. It starts to distort, you get harmonics and all the rest. But in any case, when we are discussing acoustics, we're discussing things that are quite linear for the purposes. Okay, I'm gonna accelerate a bit and wrap it up quite quickly now. Just to make sure you understand that these reflections you don't hear separately, they fuse. However, if you put a gap in there, you will actually get a sense of echo. Okay, so the echo, reverberation, it all has to do with the density of reflections. In terms of describing reverberation, we have huge complexity arising, and we're going to try to attempt to describe reverberation in a bit more detail than with a single number. But your first point of entry here is the reverberation time, which is a measurement of the duration of time it takes for the acoustical energy to drop 60 dB where there is no further acoustic stimulation. Okay, so you pump a huge amount of energy and it decays slowly away. And the duration of time for 60 dB decay is what we're looking at. There are approximations, Sabine Eyring equations. We won't really be using these. In fact, they're not hugely accurate either. I will post in the learning materials, I'll try to remember in the break, there is a really good lecture on room acoustics, which goes just that bit deeper into the acoustics, physics, maths. So if anyone is interested, I largely recommend it. Not in order to remember the equations or be able to use them, just get these terms, coming through your head and, start to use them as well. And it discusses Sabine and Eyring and when the other fails and when the one fails and all the rest. In any case, reverberation is really complex. One thing is to look at the single value, the other thing is to look at reverberation time across the spectrum, but then again, what happens in different positions in a room, many complex things happen, so things are increasingly complex. Some modeling software can cope a bit with this, although the unfortunate thing is that most of them employ ray tracing, and which is a kind of arrow shooting, so to speak. And what happens with that is that we don't really get any information on how different areas of the room behave. Okay, so in architectural acoustics, most of the time there is something to say about uniformity of a room, but typically it's not like, oh, well, this corner is horrible and that corner is much better, which is something that we are indeed interested in, when we design recording rooms or just investigate spaces for musical purposes. Nevertheless, cool stuff right there. So Sabine formula, I mean, we could go through the exercise of, okay, so what is proportional, what is inversely proportional in terms of these things, but I think I'll just skip that for now. So let's just wrap it all up with talking about rooms in general. So now that we've kind of discussed all the components needed to understand these bits, most important thing is that rectangular rooms have horrible modes. Okay, in fact, there is a measure of a room, a frequency, which separates the range where the room behaves as a resonator from the spectral range where it starts to behave like a reflector or a diffuser. And this is what we call Schroeder's frequency of a room. I won't go into much detail there. You will see in the practical I'm recommending this MROC room mode calculator, and it will spit out a Schroeder frequency as well. And this is typically something that relates to the size. So the rule of thumb for rooms in terms of musical acoustics, the larger the better, and the smaller the worse. With potentially one exception, which has to do with pressure zone. Okay, so actually if we look, I don't think I have this detail here, or do I somewhere? In one of the books you can, if you're interested, let me know and I'll find it for you, those chapters. In fact, I think in Newell's book, I don't know if I've hammered on this enough, but Philip Newell's book, Recording Studio Design, should be the one. If you just want one book to take with you, you know, least mathematics, a lot of anecdotes, very interesting, and a lot of tech as well. The point is that you can actually divide the room up in broadly four different ranges in terms of its spectral response. And at the bottom of the range, we have the pressure zone. And the pressure zone means that the frequency, the frequencies of the acoustic signal are very large in relation to the room, right? So the room is just a fragment the size of the bass frequencies. And if you're operating in this range, the room acts as a pressure zone, so you don't get waves in different phase in different parts of the room. So the whole room is pumping, so to speak. You don't get this kind of modal thing where, you know, there it's high pressure, here it's low, and then they interchange 30 times per second. That's what happens in a normal room. If the room is too small, it's all a pressure zone, so the whole thing pumps as it is. And it's the interesting thing that the range where room is a modal resonator, so where the modes are really active, that's the worst, the least flat, spectrally flat range of the room, because you have a few modes and a few notches, and they are horrible. But in the pressure zone, so when you go below the lowest resonance frequency of the room, below the lowest mode, you actually get a flat response back again. Because there is nothing that can really happen in such a small room for such a long wave. And I've actually experienced this back in the day. I didn't even study acoustics back then. I was just loving speakers and soldering and programming and that kind of stuff. And I had a room where the breadth of the room was really small. I could hardly fit. If I remember right, I had a kind of a bed, like a single bed, and a desk, and the distance was such that I could from the bed sit at the desk. So not even 2 meters, I think, like really narrow room. And that was the only way to put it up, really. It's a small room, so I had the speakers there on the desk, and I was sitting on the couch, and I was surprised, what the hell? The bass was so clean. And I didn't even have decent speakers back then. The bass was so clean. And then later, years later, I realized, oh, bloody hell, it was a pressure zone thing, because the bass is really clean below the lowest room mode. Now, nevertheless, this is a rare occasion, and I don't even know if I should advise you to record double bass in a phone booth. You know, try it, by all means. But the point is that normal size rooms actually have the worst in the bass, right? So the modal frequencies are all in the bass, and that's why we suffer with bass. And one way to get rid of this is to get a huge room. Okay, because then the modal part actually goes down into the subs, and the bass become progressively cleaner. I mean, unless it's hugely reverberant, which messes things up on another level. Okay, so that's what happens. In rooms, normal size, we get these resonances. So I've mentioned this MROC room mode calculator, so it will be part of the practical. You will have some fun with this. So I'll just completely wrap it up now. Obviously, as usual, I wasn't quite as concise. The terms that are important are axial modes. So axial modes of the room are the ones that involve two opposite walls. Okay? You can calculate these frequencies. Here is an example. You will see these in a bit. Then we have tangential modal paths, tangential modes, which means that the resonance is set up between four walls, or in other terms, you get the resonant pattern in a plane, right? So I can put a plane in a room such that it reaches four walls, so you get a kind of a circular thing. You see, because for a resonance to exist, you need this circular path, right? That's the point. That's why if you break the circle, if you put something absorptive in the path of the mode, you are attenuating it, right? So you need a resonant circle with very reflective points, and then you also may have an oblique modal path such that it touches all six walls. You can calculate this. We have lovely online things for this. The interesting thing to note is, so you see there is the region with a lot of peaks and troughs, and then comes some more of a flat response after that. And what is really important is that the density of modes increases. The density of reflection increases in a room, which is something that early reverberators couldn't do. So if you're into signal processing, building reverbs, that's a crucial thing, the increasing number of reflections. And then we have the modal density. So there's different ways you will see in the calculator how you can assess the quality of the room. We will talk about this more when we get to recording rooms and control rooms. Okay, see if you can do the tasks for next week, and that'll be that. So what I have for you then is the practical sheet is online. The boxes are in the usual rooms. Take a break as much as you want, as much as you need. Then go to a room with your mates and start doing the things. Okay, I won't introduce it now. It should be self-evident, or it should be challenging. And I will walk around and help you out. All right? Cool. That's that.